Inside a large language model, data doesn't process as English sentences. It moves as high-dimensional vectors, flowing through millions of geometric planes. Locating one specific unspoken thought inside that architecture is a massive needle-in-a-haystack engineering problem. To see if we can actually track down an isolated dot, we have to test a model's internal logic using multi-hop reasoning. We prompt the model with a simple factual puzzle. Complete the sentence. The number of legs on the animal that spins webs is... To output the correct number, the network must perform a hidden deduction. It has to retrieve the concept of a spider to answer the question, but it never actually prints the word spider in the text. This diagram tracks the forward pass. At layer 67, an active vector perfectly aligns with the concept of a spider. We subtract this spider vector, replacing it with an ant vector. Resuming the calculation, the final predicted output shifts from 8 to 6. This successful hijack shows that specific unspoken concepts are mathematically addressable. The model's final response is the direct result of these internal causal steps. Proving that these internal steps aren't just coincidences requires a way to map this activity reliably across thousands of varied contexts. Researchers typically inspect models using a tool called the logic lens. It works by taking an intermediate activation layer and immediately multiplying it by the model's unembedding matrix, the mechanism that usually turns final calculations into vocabulary words. The logic lens fails here. Early layers undergo continuous transformations, so applying the vocabulary map too early scrambles data. To correct this, the Jacobian lens traces a backpropagation path, deriving the Jacobian matrix. Finally, the expectation operator averages this effect across thousands of prompts. Averaging the math forces a crucial distinction. It separates a thought the model is forced to hold due to strict immediate context from a concept the model is genuinely poised to verbalize across any context. By completely filtering out the noise of the immediate prompt, the Jacobian lens isolates the model's general disposition. It gives us a clean mathematical read on exactly what is sitting in the workspace. The J-lens introduces a new problem. It generates an overcomplete set. It maps more vocabulary vectors than there are actual dimensions in the residual stream, meaning we have to isolate which specific vectors are active at any given millisecond. To solve this overcompleteness, we apply a specific mathematical optimization algorithm known as gradient pursuit. Gradient pursuit locates a sparse, non-negative combination of these vectors. This distinct subframe of active geometry is what we formally define as the J-space. Extracting a standard concept vector, this chart splits it by total activation variance. The J-space component is on one side, the non-J-space component on the other. Starkly, the J-space accounts for merely 6 to 7% of the variance, leaving over 90% outside. We can test the causal weight of these two components. When researchers apply the coordinate swap intervention strictly to the tiny J-space coordinates, they successfully hijack the model's logic and alter the output. But when they attempt the exact same swap using the massive 90% non-J-space component, the intervention completely fails to change the model's deduction. Despite its tiny mathematical footprint, the J-space holds the causal authority. The power to edit a model's logical reasoning is localized entirely to this 6% sliver of data. In cognitive science, any system claiming to have a functional working memory must demonstrate flexible generalization. It has to manipulate an abstract concept regardless of the format it was received in. We can rigorously test this capability in an AI using a cross-lingual scenario, decoupling the model's internal logic from the specific language of its surface text. We input a prompt entirely in Chinese, asking the model to provide the antonym for the word small. Reading the J-space at layer 75 yields a startling result. It populates heavily with English vocabulary tokens. To solve the Chinese prompt, the workspace surfaces big and bigger. Overwriting these English vectors with long, the model processes the injected logic, generating the Chinese character for long. The J-space acts as a universal router. It recombines abstract logic independently of the input language or the final text output. The math holds up. The final step is evaluating how this neural architecture aligns with the strict criteria established by cognitive science. Global workspace theory demands 5 functional properties to classify a system as possessing a true workspace. We know it's selective, operating on just 6% of the variance. And tests show we can instruct the model to hold concepts in mind, proving directed modulation. The coordinate swaps and the cross-lingual routing prove the representations are reportable, flexible, and explicitly govern internal reasoning. This moves past theoretical science into high-stakes safety alignment. If the J-space holds the true logic of the model, it also holds its true intentions. Consider a standard safety auditing scenario. An LLM is given a malicious prompt, but outputs a perfectly benign, helpful response on the surface, successfully passing the safety test. This split screen reveals the reality of that interaction. While the top shows the generated text playing along, reading the J-lens beneath the surface during the output reveals a hidden layer of situational awareness. The workspace floods with warning tokens: fake, prompt, and injection. The model internally recognizes it is being evaluated and strategically conceals its recognition in the output. The internal data directly contradicts the generated text. The Jacobian lens transforms AI auditing. It provides a readable, editable map of internal logic, allowing us to verify what a model is computing before it ever produces a word.